All right, so now we get to do a shorter and more focused talk on a singular topic, and we're going to talk a bit about protocols. Goals for the session: we're going to try to define what a protocol is. We're going to try to talk a little bit about that, which protocols are used in DCS versus SCADA, and the topic that Marty covered. We'll talk about some of the challenges with securing these protocols. Dale mentioned in his, the last session, insecure by design. We'll also talk about insecure by implementation. As we get towards the end of the presentation, we'll talk a bit about how do we actually add cryptography to these protocols, what are the risks, what are the trade-offs, et cetera. And sort of at the very end, I'll make kind of a blind stab and some predictions about the future. What you won't learn in this session, I'm not going to get into any great technical depth. This session is a bit of a challenge for me because I'm more of a technologist, security researcher, software engineer. So Dale got my first revisions of the slides. Every comment on every slide was too technical, kind of all the way down the entire deck. So raising this up to the strategic level and thinking about what are the decisions that people deploying these protocols have to make to address risk, that was a challenge for me in developing this presentation. So we'll see how I do. And then as far as protocols go, there's a whole slew of IT protocols that get used in OT. Right? You've got all the ones mentioned on this slide. We're not going to go into any depth really about how those are used or applied because that would be massive presentation, right? We're really going to talk about the protocols that are purpose-built for the industrial control systems themselves and not the IT protocols. So definition, it's a bit of a tautology, but it's a communications protocol used to monitor and possibly control a process. Sometimes these protocols get deployed in kind of read-only modes, sometimes in write-only modes. They don't always completely close that control loop that Marty talked about, where you're both reading values and writing things back to the process. Why would you deploy these protocols? Well, typically, they're replacing those sort of analog things that Marty talked about, like using pressures to signal value levels or so forth, or 4 milliamp control loops. We're now replacing those things with sort of networked digital equivalents so that we can use those protocols to get those values up to our human-machine interface, so we can store them in a historian, so we can later look at what the process has been doing over time. And then some schemes that in control systems actually rely on distributed control. So you might have logic in multiple places that need sort of measurement values from all the different process elements. So you could think of a scheme where everybody's talking to everyone about what they're doing and everyone's making decisions all at the same time. So ICS protocols, in addition to kind of acquiring those values, they also transport commands to endpoints. So you might use a protocol to change like a kind of binary component of the system, say open a valve or close a switch, push a button, something that's just on or off. When you're talking about this sort of more wet process control, like Marty talked about, you have a concept of set points. And set points are sort of commands that you send to the process, but they're not discrete on and off. It's more like a level or a measurement, like fill a tank to a certain level, charge a battery to a certain percentage, things that can kind of vary between a low limit and a high limit. That's a set point. So you'll hear that used kind of all over the place in vendor documentation and so forth. So with that definition out of the way, I'll talk a little bit about history. So the sort of digitization of these protocols goes all the way back to like late 60s, 70s-ish somewhere. And originally, these protocols sort of acquired data through a process called polling. So you'll hear about polling constantly when you talk about these systems. And what polling is sort of the component that wants to know about a measurement value is just sort of periodically on a schedule asking that piece of equipment for what's the value now, what's the value now, what's the value now, and that remote component is sending back the current value, okay? And that period for that polling is usually kind of determined by a couple of factors. Sort of the legacy equipment used to all be networked via serial, those DB9 and DB25 connectors that Marty mentioned. And those are pretty low throughput communication links. 1200 baud, 9600 baud, really low data rates. And that stuff still, exists everywhere today because of sort of the long shelf life of industrial components. I mean, you'd be surprised to know how much infrastructure and electric power is still kind of leased line 1200 baud or 9600 baud modems. And when you have very low throughput, you can only ask for things so often, maybe once every 10 seconds even. And you might prioritize the sort of different things you care about and ask for high critical information at a higher frequency than, say, low criticality information. But, as time has sort of moved along, these sort of serial networks have been converted to various IP protocols, UDP, TCP. Some protocols rely on sort of their own bare Ethernet frames for kind of transmitting information around in a non-routable fashion. But that transformation is certainly not complete. Tons of facilities still have tons of serial stuff out there, and it'll be around for a very long time. You can't talk about protocols without talking about Modbus. I know this has probably already been mentioned in the 2 prior talks. So Modbus was a big deal back in the late 70s because it was the first protocol to really kind of be standardized so that anybody could download a document that described the entire structure of the protocol end to end. And you had multiple vendors implementing it in mostly similar fashions, sometimes with some proprietary flair like that function code 90 that Dale talked about in the last presentation. I would say for the purposes of this presentation, if you wanted to take on sort of a deeper learning project, getting a hold of some Modbus PCAPs and dissecting them and looking at how the protocol works at a low level is a really good research project because the protocol specification itself is only 50 pages long. You really can kind of scan through it on a flight or in an afternoon. You can get a pretty good understanding of how it works. The ones and zeros actually map to things. And with those ones and zeros, that's actually a really key point about most industrial control system protocols is that they don't give you any context over the wire about how those values map to the process. They're just sort of opaque ones and zeros or values or numbers, okay? All that context for saying, that this bit at this position in the message represents whether a valve is open or closed, and this number here happens to be a voltage, that's not actually contained in the protocol over the wire. That's usually information that's stored, either in the communication server that's talking to all these components or, in an engineering workstation somewhere that manages all the configuration. And that's really important to understand for, protecting these systems from an attacker. Attacker typically has to do quite a bit of reconnaissance to be able to sort of map what's in the protocol to accomplish whatever their objective has to be. So for a long time, this community has kind of relied on security through obscurity. Even if an attacker gets in, they're not going to know what the hell to do because it's all just sort of ones and zeros flowing over the wire. And a lot of the protocols still are kind of opaque, but some of the newer ones that have these rich domain models for specifically industries are becoming increasingly descriptive, which is interesting from an attack perspective. So if you think of Modbus as sort of the basic capabilities of an ICS protocol, protocols over the years have really specialized and added all kinds of rich features for various reasons. Okay, and so we'll go through some of these bullets and talk about why what's wrong with Modbus. Why not just use Modbus for everything, right? It can read values, write values, it can do everything you need to do, and you'll see some just insane control schemes mapped to just the very basic primitives in Modbus. One of the earliest drivers was just that, Modbus only has 16-bit values. What if we want to report floating points or doubles or 32-bit values? And you just see insane ways that people map, different types of numbers into 16-bit registers, and nobody does it in the same way, and nobody documents it. And every time you get, a Modbus data sheet from somebody, you have to figure out how did they map these things into Modbus. So some of the newer protocols have, specialized types for floats and 32-bit numbers so that people all do things in the same way. And that leads to better, interoperability and people are happier, right? When you start talking about SCADA versus DCS, SCADA systems are generally much more bandwidth sensitive. They have lower bandwidth because they're going out to, sites over a broad geographical area. So those protocols, the features that they build into them, are generally around bandwidth minimization. So instead of asking for all the values every time you communicate with a remote asset, you're generally only requesting things that have changed with a SCADA protocol. What's changed since the last time I polled you? And you'll just get back those sort of deltas or changes. And maybe every once an hour you'll say, well, what's the current state, just to make sure you didn't lose synchronization. So when you think about SCADA protocols, really think about bandwidth minimization and error detection for less reliable networks. Two of the biggest protocols there, you probably heard about DNP3. That's more of North America. If you're in Europe or Asia, then the IEC 104 series of protocols will be the SCADA protocol of choice. Another reason that things have sort of specialized, and this is more on the sort of DCS side, is using sort of publish subscribe architectures. So if you're in a DCS, a lot of the protocols there will be these kind of very chatty UDP multicast type protocols where they're constantly sending out their values to a group of subscribers. And in the DCS, where you're on a local area network, you're much less concerned about bandwidth than you would be in SCADA, so you can afford to constantly being broadcast to your subscriber group all the things that are happening within the process, all the values that are changing, et cetera, et cetera. There's some really nice consequences of using those types of architectures because you can kind of break up those sort of brittle one-to-one mappings. You don't have to configure in two different systems that this point maps to this point. I can add another consumer or publisher of that data without having to change everybody else's configuration. And then finally, the sort of last area where I'd say that protocols have really specialized over 5 or 6 decades of digitized control system protocols is developing industry-specific models. So instead of just having these sort of registers, like, register 0 is a voltage, 2 is a current, 3 is a frequency, and having to understand that, they've developed these sort of industry-specific models where the protocol messages actually have structure that describe the process. So good examples of these would be, ODVA's SIP. They actually have concepts in there for things like motion control and synchronization, things you might really care about if you're a manufacturing plant. And then over in electric power, there's the IEC 62850 series of standards, and they have these huge, rich models that describe things in electric power. It's like you might have a node that says, well, here's 3-phase current and voltage for, current and voltage transducers, something specific to that industry. And from an attacker's perspective, those sort of self-describing protocols that provide all that context are a much richer target than protocols that are sort of less descriptive or completely opaque, where you'd have to compromise some engineering plans or something else to be able to do anything to the, to have enough context to do anything to the process. So this was my stab at sort of a very 10,000-foot view of some important protocols and sort of what industry verticals they're used in. And I tried to also attempt, on the left, you'll see DCS, on the right, you'll see SCADA, to kind of capture that split between those two different types of control systems. It's by no means meant to be comprehensive. There's certainly protocols I've left out. If you're talking down at the level 0 or 1 level where you have those sensors, you have things that are called field bus protocols. And I know that Marty and Dale mentioned HART. There's also something called Profibus out there, along with a whole slew of others. When you step up from the sensor level, or even at the sensor level, you have Modbus. It's ubiquitous. You'll find it everywhere. When you start talking from HMIs down to things like PLCs, you're probably using one of these protocols like Siemens S7 if you're a Siemens shop. If you're an Allen Bradley or a Rockwell shop, you're probably using Ethernet IP. There's also a whole slew of vendor proprietary protocols still used in DCS. So, Emerson has their own protocol. Yokogawa has their own protocol. They tend to be sort of, less well documented than these standards like Ethernet IP. And then sort of at the top and going from the control system up into corporate, frequently you'll see things like OPC, OLA for process control, is still quite ubiquitous. You'll see that everywhere on the DCS side. On the SCADA side, you tend to have these protocols at the wide area network level that do the bandwidth minimization for you, that are really good for going out to hundreds of sites over less reliable communication media like microwave or dial-up modems, or just really low bandwidth Ethernet radios. Those would be DMP3 or 104, like I mentioned. In electric power, we have some specialized protocols at the substation level, 62850, and we have specialized protocols for connecting control centers to control centers that run over IP infrastructure. And then, of course, down inside substations where it's an actual facility, you could think of it like a manufacturing facility. A substation has its own LAN. You'll still see things like Modbus and proprietary protocols and things like that. This isn't to say that all the verticals I have on the left don't have SCADA. You'll see SCADA in oil and gas and chemical. They're not all pure DCSs. And you'll notice that power has been split into two verticals there. Power generation tends to be more DCS, whereas power transmission and distribution, which is the TND, tends to be more SCADA oriented. So this slide is not going to capture all the nuances everywhere. So Dale already mentioned this, and I'm glad that I heard that they coined the phrase back in 2012, which is insecure by design. Well before that, yeah. So as applied to protocols, what that means is that these protocols were designed without any cryptographic security. Okay, and I say cryptographic because just putting usernames and passwords and then sending them in clear text over the network doesn't count. That's not security that's going to prevent an attacker who has network access from compromising things. And I won't go harp on too many of these bullets too much because Dale already mentioned frequently the easiest way to exploit a single device, not necessarily the whole process, but a single device, is just to read the manual and see what the protocol is capable of doing. And if you've read the manual, there's nothing in there, you can probably find some undocumented features that can also do it for you that don't have cryptographic security. And historically, there have been sort of various arguments for not putting security into these protocols. I've reported a number of bugs to vendors, and once you get past the initial friction, which is, you're a horrible person, why are you doing this to me? The second thing is, well, all of our customers are on private networks, so none of this matters, right? And then you start taking them through various, attacks that have happened in the industry and educating them a little bit. And, well, if there's not attackers, there's always insider threats and these types of things, and the lights start, popping on. And, if you got an asset owner in the room, they'll tell them, you can't tell me how to design my network. Only I can do that. I want secure, equipment from you. Probably the biggest argument historically, though, has been impact on availability. So if you've ever wondered why, HMIs and operator workstations all have the same password, it's so that, somebody who's completely in a frenzy because something is going wrong doesn't want to have to worry about logging into something when they need to do something on an engineering workstation or an HMI. Same thing with adding security into protocols. What impact is adding cryptographic keys and having to do all that management potentially going to have on the availability of that monitoring? It's something you can't ignore, and it's something I haven't seen vendors really address yet when they talk about adding security. And we'll go into a little more detail about this later in the presentation. But a lot of the bugs that we find in these protocol implementations, I would just call them junk bugs, because they're not significant because they don't add any more capability for an attacker than what they can already do just by using the features of the protocol. So that leads me to the second topic, insecure by implementation. And I think I'll just skip to the bottom and say that the bugs that matter are the ones that allow you to do something important to the process that you couldn't already do through the protocol itself. And I'll give some examples of that on the next slide. One thing that's important to note, though, is that protocol implementations in this space have defect rates that are way higher than under other industries. Way higher than telecom, way higher than web servers and web clients and things we use on the internet every day. And there's various reasons for that. I mean, some of the big ones I've got up here, reasons like, it's really hard for security researchers to get a hold of some of these equipment. They're super expensive. The vendors protect their crown jewels. They only give them to their, privileged customers. So a lot of them just haven't received the scrutiny that you would see for things that get used on the internet. And the second reason is that, asset owners just haven't asked for the security. And, as the saying goes, you get what you pay for, right? So no one's asking for these things to be tested, and asset owners aren't doing the their own sort of due diligence and testing before making large purchases. It's just taken a while for that sort of pressure to mount and for vendors to provide secure implementations of things. So I'll give you one example of bugs that matter. So back in 2012, Chris Sistrunk and I were here at S4, and we were talking about bugs in SCADA masters, so the communication servers that talk to many, many remote assets in the fields, like remote terminal units or gateways and substations. Nowadays, they talk to lots of pole-mounted equipment like capacitor banks on lines or voltage regulators. And we found that, there were quite a few bugs in the SCADA masters themselves. You could send malformed or, intentionally malformed packets from the field back up to the master and crash the master system. That's important because, in a perfect world, if you've done that network segmentation that Dale talked about where site A can't talk to site B and you have everything locked down and only those protocols are allowed, if there's a bug in the master, you can just pretend to be that field asset and crash the system. And for particularly some of those bad bugs might allow remote code injection, where you could actually get into the control center or run malicious code on the control center by exploiting a bug in the protocol master. In an ideal world, if there were no bugs, the worst you could do would be just to give false measurements for a single site, right? If you've done all your whitelisting and network segmentation correctly. But the minimum sort of impact would be a denial of service, but it wouldn't be just a denial of service for that one remote field asset. You could potentially kind of knock out visibility to all the assets that server's talking to. So that's an example where the consequence of the bug kind of exceeds the capability that the system was intended for. And that's an example of kind of a bug that matters. So with all that talk about the problems, how do we secure these protocols? Over the last 10 years, I would say, the approach mostly has been for bolt-on solutions. So things like packet inspection stuff, which is really nice because it's completely passive. You can just plug into a network tap and you can potentially, detect an adversary on your network. It doesn't necessarily prevent an incident unless you get there in time, right? You notice it in enough time. And then there's also firewalls that can actually prevent incidents because they're inline, actually on the network, isolating that component. They actually understand the protocol, like they're breaking apart Modbus and looking, they can tell a read from a write and they can block the write, right? These solutions are very helpful and they're great from the availability standpoint, and particularly the sort of passive network security monitoring, because they don't affect availability. They can just passively hang off a network tap and they're not going to cause the process to crash or go down. But ultimately, they're somewhat limited. If you already need a certain capability, so you have to let writes through because component A has to send writes to component B, there's not much they can do, right? They have no ability to tell that the person that sent the write was the person that should be able to send the write, right? All they have is the layer 2 information, the MAC addresses, the IP addresses, and that can all be spoofed, right? So ultimately, those solutions are ultimately constrained. So I think sort of the last level of defense in depth is going to be adding security to the protocols themselves, where you actually sort of use cryptography to put private keys on the equipment and on the things that want to talk to them. And there's various ways of doing that we can't get into in this session, but I'd say that's sort of the final frontier and the final layer of defense in depth for network security. So I'm going to talk about 3 ways in which that's being done right now. The first and most common way is just to use protocols that we're already all familiar with on the internet. So transport layer security, or TLS, the same thing that protects the communication from your web browser to your banking site. We can apply that within industrial control systems, and lots of standards bodies have kind of specified, here's how you use TLS for our particular protocol. So a standard body called ODVA has a document out there that says, here's how you apply TLS and DTLS if you're using UDP to Ethernet IP. Schneider Electric has been pushing a secure version of Modbus that says here's how you secure Modbus. It goes a little bit beyond that because they're actually like embedding access control lists in the certificates, which is kind of neat. This person with this certificate should only be able to perform write access to the device. In the electric power industry, we have a standard from the IEC that basically says here's how you apply TLS to protocols in the electric power industry. There's pros and cons. The pros of this approach is the protocol is mature. There are tons of libraries out there, both open source and commercial, for doing this. You don't have to have vendors don't have to be specialized in writing secure code because they can use a third-party library to do the cryptographic operations and add the security. But in my opinion, there's quite a few cons. TLS was fundamentally designed for the World Wide Web, and the Internet Engineering Task Force that monitors TLS has been progressively making TLS much more aggressively focused on encryption at all costs and privacy of endpoints at all costs. So in TLS 1.2, the current version, you had the option for doing authentication only without encryption. So you could cryptographically prove that endpoints who they said they were, but you could keep the actual traffic clear text. So your network security monitoring platform could kind of see what was going on. That's not going to be the case with TLS 1.3 and going forward. They've really stripped TLS down. They're worried much more about privacy of individuals on the internet. And a lot of the design decisions they're making with the new version of TLS are not necessarily good design decisions for private networks where you own all the infrastructure. You don't care if your PLC has privacy necessarily. You care a lot that somebody who's not trusted can't send commands to it, right? So I would say the design goals with TLS are starting to diverge from what might be good design goals for a secure protocol in this space. The second approach is bolt-on security. A lot of protocols have extension points where you can add new objects and features. So we've seen this with the SCADA protocol DNP3, where they've actually embedded security into the protocol. The pros of this is that it works in IP and serial. You don't need to change anything. You can actually do phased migrations where some of your endpoints are insecure and some are secure. That's really cool if you have just, you're a water utility and you have a 900 megahertz radio that's just kind of round robin talking to all these different endpoints, because you don't have to upgrade everything at the same time. The cons for this approach are it's really complicated and there's a high cost for development and testing, and you're only securing one protocol. So ultimately, you're going to pay a lot, and you're going to have to learn a lot just to secure a single protocol. So I personally I haven't seen a lot of adoption. My personal opinion is this is probably not the route the industry is going to go for securing most systems. The approach that I'm more bullish about is sort of modern wrappers. So think about, what are the good things about a wrapper protocol like TLS, and how would we build a protocol that's more purpose-built for this kind of space? So that's kind of what I'm currently working on. Compared to TLS, we're kind of focusing on, we want to be able to provide encryption if necessary, but we also want authentication-only modes. We want really lightweight certificates and cryptographic primitives that are kind of friendly with embedded systems, because we have a lot of embedded systems and low CPU stuff in industrial controls. So there's a presentation you can find on SSP21 from actually the last 2 years at S4 if you search on YouTube, if you're curious about learning more about SSP21. But ultimately, with all three of these approaches that I mentioned, there's going to be limitations and impasses. I already talked a little bit about the impact that having a key timeout or having your certificate authority or something go offline, it's pretty unacceptable that the security you add, would result in affecting the availability of your control system. That would be a deal breaker for most people. And I think this is where people kind of thinking about protocol security really need to focus their attention over the next couple of years, is how do we add security to these protocols without affecting availability and making asset owners confident that that's really truly going to be the case. Secure protocols are also just not a silver bullet. You'll probably hear more from Rob or others later in the day about in-destroy or a crash override, which is the attack against the Ukraine a couple of years ago. In that particular example, they compromised the server, the communication server, which would have the cryptographic keys. So, if you let your keys get stolen, secure protocols don't help you. And in a lot of the attacks, people have gone after the communication server. So if you don't harden that attack surface, these secure protocols just aren't going to help you. Briefly, because I'm running out of time, talk about crossing security zones. if you talk about crossing from the OT network into the enterprise and through the DMZ, some of the most common protocols are going to be things like historian protocols or OPC. Some industries have their favorite protocols for transporting things. You'll see DNP3 going across the DMZ and electric power. In some industries, we're starting to see ICS protocols actually running over the internet. So in electric power, we do this thing called demand response, where third parties separate from the utility provide the capability of kind of shutting off load when demand reaches a peak, right? And they roll all these different sites up into what they call a virtual power plant. So utilities actually interface with lots of third parties now over the internet. And frequently they're wrapping something like DNP3 and TLS, or there's a VPN connection with IPsec. And at the moment, that total load is pretty small compared to their base generation. But as it becomes larger and larger, it's going to become a problem if people perform denial of service attacks on that. And Dale also mentioned predictive maintenance, where you're pushing up data from your system to a vendor so they can look to see like when equipment needs to be replaced. So protocols are certainly becoming more and more pushed out over the internet. In terms of the future, I think that you are going to see a lot of IoT technologies start coming into ICS, if nothing other than to kind of speed up the pace of innovation. So if you've been monitoring IoT, you've heard buzzwords like MQTT, which is like a pub sub protocol. I'm actually working on a project with a major electric utility where they're actually building a new standard called OpenFMB, Field Message Bus for microgrids. And they're using IoT technologies that have open source libraries, and you can build a client to talk to one of these systems in an afternoon, just because you don't have to reinvent the wheel and kind of build everything from scratch. So I think that we are going to see more and more of that over the next couple of years. And I really hope that there's going to be more innovation around the key management part so that we can add security into these protocols themselves. So that's my predictions and hopes for protocols going forward.